Let's take a look at an introduction to hypothesis testing, an important part of statistical inference. Let's look at an example to start. Suppose our friend Pete claims he can guess the suit of a randomly selected playing card more than 1/4 of the time on average. If one is simply guessing randomly, then there is a 1/4 chance of guessing correctly on any given card, and Pete says he does better than this on average. We decide to make Pete back up his claim, and we make Pete guess the suit of a randomly selected card 100 times. So if Pete is purely guessing, on average he'll get 25 correct. And he guesses correctly 28 times, and he might be happy about that and say that shows that he was correct. But does this really provide strong evidence that Pete has a probability of greater than 1/4 of correctly guessing the suit of a card? If Pete is simply guessing randomly, then on any individual card he has a 1/4 chance of getting it correct, and the number of correct guesses in 100 would follow a binomial distribution with parameters n being 100 and p of 1/4. And that binomial distribution is given here. It is the distribution of the number correct if someone is purely guessing at the suits of 100 randomly selected playing cards. Here the possible values go all the way out to 100, but the probabilities get pretty small, so I've chopped it off here at 50 just to make the plot look a little nicer. And we might ask ourselves this question: what is the probability of getting 28 or more correct when guessing randomly? Pete actually got 28 correct. But had he done even better, got even more correct, we would have thought that was even greater evidence in favor of his claim. And so we're going to work out the probability that Pete would do as well as he did, or even better, if he's simply randomly guessing. And so we could use the binomial formula, or I sped things up a little bit using software. So if x is a random variable with this distribution, the probability that that random variable takes on a value bigger than or equal to 28 is approximately 0.278. So if Pete has a 1/4 chance of guessing correctly on any given card, the probability that he'd do as well as he did, or even better, is approximately 0.278. And that probability is not very small, so it is not unlikely to get this many correct due to chance. And so we would say that there is not strong evidence that Pete has better than a 1/4 chance of correctly guessing the suit. We just informally conducted a hypothesis test of the null hypothesis that P is equal to 1/4, or in other words, that Pete does just the same as someone who is randomly guessing. And we tested that against the alternative hypothesis that P is greater than 1/4, or in other words, that on average Pete does better than someone who is simply purely guessing. And based on what we saw, we did not have strong evidence against this null hypothesis. But suppose instead Pete had guessed correctly 44 times. 44 is way out here, a very unlikely value to get if one is simply randomly guessing. And the probability of doing as well as that, or even better, probability that a random variable with this distribution takes on a value that's greater than or equal to 44 is 0.00027. And that is approximately 1 time in 37,000. So it would be very, very unlikely to do as well as Pete did, or better, if he is simply randomly guessing. Since this probability is very low, one of two things occurred. Pete is simply guessing with a probability of success of 1/4, and we witnessed a very unusual event due to chance. Or Pete is truly guessing the suit more often than 1/4 of the time on average. Or in other words, the null hypothesis is true, and we witnessed a very unusual event, or the null hypothesis is false. Now, this doesn't have to mean that Pete has ESP or something like that. It could be something simpler, like we've designed our experiment poorly and we're inadvertently giving away information when we look at the card, or Pete has a friend standing behind us, signaling him sometimes. But regardless, we have some strong evidence against this null hypothesis. In general, in hypothesis testing, we turn a question of interest into hypotheses about the value of a parameter or parameters. We create a null hypothesis, denoted by H0, and an alternative hypothesis, denoted by HA. This null hypothesis is sometimes called the status quo hypothesis. It is the hypothesis of no effect or no difference. The alternative hypothesis is sometimes called the research hypothesis, because it is often the hypothesis that the researcher is trying to show. These ideas are a little bit abstract off the start, but it becomes much clearer as we work through examples. Then we calculate an appropriate test statistic that is based on sample data and determine how much evidence that gives us against the null hypothesis. And if the evidence against the null hypothesis is strong enough, if it meets a certain significance level, we can reject the null hypothesis in favor of the alternative hypothesis. We might also say that the evidence against the null hypothesis is significant. We might be interested in the question, do men and women have different average salaries after graduating university? Here, the appropriate null hypothesis would be that there is no difference, or in other words, the true mean for males is equal to the true mean for females. And the alternative hypothesis is that the null hypothesis is wrong, or that there is a difference between males and females. Now, we might phrase that alternative hypothesis a little bit differently depending on the setting, but more details on that later on. An important point to note is that we make hypotheses about parameters and never about statistics. So you should never see something like this, that x bar for males is equal to x bar for females. The only place you should see something like that is in a video explaining that you will never see anything like that. We make hypotheses about parameters and not about statistics. Or we might be interested in a question like, do 3 different production processes all have the same variance? So the null hypothesis is going to be that there is no difference, that those 3 population variances are all equal. And the alternative hypothesis is going to be that that is wrong, that those 3 population variances are not all equal. Or we might be interested in this question. Is the average weight of a certain type of candy bar different from the desired 58 grams? Well, the null hypothesis would be that the true mean is equal to 58 grams. And the alternative hypothesis might be that the true mean is different from 58 grams. Depending on the setting, we might choose a different alternative hypothesis. We might choose the alternative hypothesis that mu is actually greater than 58. Or in a different type of situation, we might choose the alternative hypothesis that mu is actually less than 58. The appropriate choice of alternative hypothesis depends on the setting, and we'll look at a few examples of that a little later on. But many questions remain that could not be answered in this brief introduction. For a given problem, what are the appropriate hypotheses? What is an appropriate test statistic to use? What is an appropriate significance level? When will we say that there is significant evidence against the null hypothesis? And does our data give us significant evidence against the null hypothesis? We're going to use 2 approaches in hypothesis testing to answer that question, the rejection region approach and the p-value approach, but much more on that later. And what is an appropriate conclusion to the practical problem at hand? In the end, we want to tie this into the questions we are trying to answer. In this video, our conclusion simply would have been, Pete, we do not have strong evidence that you are doing better than someone who is simply randomly guessing. Coming up with the appropriate conclusion in the end is very, very important, as the whole idea here is that we are trying to answer some questions of interest.